Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. So today I'm going to discuss about the fission and as well as fusion. Okay. So this is part 3 video of the nuclei chapter, and if you want to go visit, you can visit our part 1, part 2 video for this chapter. So here I will discuss mainly about the nuclear energy and see, nuclear energy is the energy released during the transformation of the nuclei with less total binding energy to the nuclei with the greater binding energy. So let us consider let us consider this is an atom and this is a nucleus, right? Nucleus, and this is your atom. Got it? Now what happened whenever there is a breakdown or combination of nucleus, whenever there is a changes in the form of the nucleus, so what will happen? Nuclear energy will be released. Nuclear energy will be released, right? Now, the release of the nuclear energy of there are two way by which we can obtain the energy, and two distinct way of obtaining energy from the nucleus are nuclear fission as well as nuclear fusion, right? So let us go one by one. Now, first of all, I will talk about the nuclear fission. Nuclear fission is the phenomena of splitting of heavy nuclei, usually a atomic mass number greater than 2. So there is a heavy nuclei, right? And when it will split into two parts, two lighter nuclei, lighter nuclei, and basically this happen when the atomic mass number is greater than 230. Example, uranium is the example, right? So what will happen? What will happen? Uh, See, what will happen? Nuclei by the bombardment of the protons, neutron, or alpha particle, etc. energy associated with the nuclear process are about the millions times larger than the chemical process. Now let us understood here there is a heavy nucleus. There is a heavy nucleus, and when there will be a slow bombardment of neutron. So what will happen? It will strike the nucleus part, right? This is an atom and this is a nucleus part. So it will bombard. So there is slowly when it will stuck, so it will break into two parts, and this two part is this fundamental process is considered as the nuclear fission process. We can say that splitting of a heavy nuclei into two lighter nuclei is considered as the nuclear fission. In fission, a heavy nucleus like 92 to 35 breaks into two smaller fragments by the bombardment of the thermal neutron, low energy or a slow moving. For example, U2 92 to 35 plus 01 neutron gives you the beryllium as well as krypton plus 3 neutron, and this energy is being released. Now, one more very important thing which will occur, you need to understand that Q value here, Q refers to the energy released by the nuclear process and can be determined by using the mass energy reaction, that is E is equal to mc square. The Q value is equal to the difference of the mass of the product of the reactant multiplied by the square of the velocity. Now let us consider there is a heavy nucleus, and when it is got split into two lighter nuclei, so what happens? Earlier the mass was 100, let us consider now the mass was 40, now the mass was 56. So total here it is only 96 gram or 96 atomic mass unit. So where does this 4 4u gone. So this 4u is considered as the mass defect, right? So the energy equivalent amount of energy can be considered as the delta m c square. Here delta m is your 4 unit into c square, that is the speed of light. So this amount of the energy is being released, right? So the Q value is equal to the difference of the mass of the product and the reactant multiplied by the square of the velocity of the light. Now energy released per fusion of 235 uranium is 2004 mega electron volt, and the fragment of nuclei produced at the fission are highly unstable. So these are the highly unstable process, right? Now they are highly radioactive and emit beta particle in the succession until which reaches to the stable each end of the product. So what happens? This again, it may be unstable. It may be unstable. So again, it may get split into two further part. Got it? And apart from this, they are emitting beta radiation, which is which is dangerous for human. Now, what is nuclear chain reaction? In the nuclear fission reaction, there is a release of an extra neutron, right? So the extra neutron in turn initiate the fission process, producing a still more neutron and so on. Thus, the chain reaction of the nuclear fission is set up called the nuclear chain reaction. Now, let us understood by the diagram, right? Let us consider there is a uranium and there is a slow bombardment of the neutron on this. So what will happen? This uranium will get converted into two smaller particle. So let us consider two krypton and all. And apart from this, it will also release three neutron. How many neutron? Three neutron. One neutron, two neutron, and three neutron. Now, as we have more than there are lots of uranium atom. So if there is again another uranium is present like this. So what will happen? This neutron will strike this uranium. This neutron will strike this uranium, and this neutron will strike this uranium, and again this will split into three neutrons, as well as two lighter nuclei, as well as energy, right? So what will happen? Each and every one will again release three neutron, and again this 3 neutron will again multiply in 3. In this way, what will happen? This will split into the multiple process, and it is very fast process. And all this will happen within fraction of second only, and ultimately explosion will happen, which will release enormous amount of energy, enormous amount of energy of energy. But this amount of energy is uncontrolled energy, and which will destroy. So it will cause the destruction. So this is not helpful for humankind. Now, since this is your uncontrolled chain reaction, so during the fission reaction, the neutrons released are again absorbed by the fission isotopes, and cycle repeats and give the chain reaction. Self-sustaining and give off the energy at the rate of that increase rapidly with the time, leading to the large amount of the radiation. This is called uncontrolled chain reaction, and it is of no use. It is only of use for the destruction purpose. But now let us consider about the controlled chain reaction. Now it is a time to utilize this whole energy in the positive manner. So if you want to utilize this one, so what we need to do? a controlled chain reaction happens if means the reaction is controlled in such a way that only one of the neutron emitted by the fission causes another fission, then the fission rate remains constant. Now, let us try to understand that suppose there is a neutron and it will attack the uranium atom, right? So, what will happen? It will split into how many particles? Three neutron. One neutron, two neutron, and three neutron. Now, there is a boron rod, and if this is your boron rod, and if it will absorb those both neutrons, so what will happen? There will be no more split, and so there will be only three. Again, next three neutron will be released. Again, you need to absorb this both neutron by the boron rod. So what will happen? It will become a controlled reaction because it will not split and it will not release very rapid way energy. It won't release any energy very rapidly, right? So this process is considered as the control chain reaction. Such a reaction is called as controlled chain reaction, and it is used in a nuclear reactor. So there is a nuclear reactor place where you will keep the uranium, you will keep the boron rod, so that boron rod will absorb and the reaction will happen in this breed, or we can say the reactor. And after this what will happen? Energy will get released and this energy can be used for the generation of electricity and all. So this is the control way of utilizing the nuclear power energy, and to sustain the feasibility of the nuclear chain reaction depends on the multiple factor or a reproduction of the factor. It is considered as a K. So K is equal to rate of production of neutron divided by rate of loss of neutron. If rate of production of neutron is very high and rate of loss of neutron is less, so what will happen? What will happen? Ultimately, it will be explosive. So the condition for which the reactions are critical, if K will become 1, so what will happen? We can say that the operation of the reactor is critical and it is what we wish to be steady power operation. So we always want this as a, it is what we wish to be for a steady power operation. So critical condition is the steady power operation. Now, if K is greater than 1, so what will happen? The reaction rate of the reactor power increase and exponentially, and in this case, reaction is supercritical and it is can be even explode. So it is not required. And if K is less than 1, the reaction gradually stops, and thus the condition is called subcritical. So we want critical condition only. We don't want supercritical as well as subcritical. We want K is equal to 1. We want K is equal to 1. K is equal to 1, then only reaction will continue for a long time with the slow energy, or the energy will constantly come out with the constant rate. So it is considered as a controlled reaction, right? So I hope you have understood this. Now I will discuss about what nuclear reactor looks like. So from here, what you can observe, it is a device that can initiate a self-sustaining controlled chain reaction by the fissionable material, and they are used at a nuclear power plant for generating electricity and propulsions of the ship. Now let us consider there is a fuel rod and it is made up of uranium. Basically, we will use uranium only. So this is the fuel rod, right? Apart from this, what will happens? There is a moderator. Moderator means which will slow down the movement of the neutrons. So moderator, they have told that it is your moderator. Moderator means basically which will absorb energy, as well as slow down the speed of the neutron. The speed of neutron. Why it is required? Because if neutron will be very fast, so it doesn't get any time to stuck with the nucleus, and it will just go thoroughly, and there will be no reaction or no splitting of the nucleus will happen. So we want slow moving neutrons. So for that we will keep the moderator. So moderator, example of moderator is D2O. That is, it is also considered as a heavy water. So it has two work. It will slow down the neutron as well as it will absorb the energy. So let us see from the figure that it will if it will absorb the energy, and after that it will go to this one, and after that it will come like this. So what will happen? Up water coming are in contact with this will become as a steam due to its heat, and it will this steam will again pass through the steam generator, and it will used for the electric generation, and this used steam is again reused in this coolant, right? So this is the way how to generate the electricity from the nuclear power plant, right? uh, So I have already explained these things. The key component of the nuclear reactor as follows. Nuclear fuel, it is a material that can be burned by the nuclear fission or a fusion to derive the nuclear energy. And the common nuclear reactor fuel is U-233, U-235 and Pu-239. Now, nuclear reactor code, it is the portion of the nuclear reactor containing a nuclear fuel component where the nuclear reaction take place. Now you can understand that the size of the nuclear reactor is very large as well as very strong, very thick. So if you observe that the wall of the thickness of the wall of the nuclear reactor, so it will be very thick. It will be very thick, right? It will be very thick, right? Now next is your moderator. It is a medium to slow down the fast moving secondary neutron produced during the fission. So I have already told you that if moderator will not be there, so it won't able to slow down the fast moving neutron produced during the fission. Heavy water, so graphite, deuterium, paraffin, etc. act as a moderator. So most commonly used moderator in India is nowadays is heavy water only. Now the control rod, it is used in a nuclear reactor to control the rate of a fission, uranium and plutonium. So these are made up of chemical elements capable of absorbing many neutrons without fissioning themselves, such as silver, indium, boron, cadmium. So boron, cadmiums are most commonly used control rod. So I hope you have understood this. Now the coolant. Coolant, it is a liquid used to remove heat from the nuclear reactor. So you know that this is a nuclear reactor, so there will be a lot of heat will be produced. Now how you will use the heat? So just put a coolant. So coolant will absorb the heat, and again it you pass it through the steam or water. So it will this water will again get converted into the steam. See here from this figure you can understand how this will happen. So coolant actually what is the function of the coolant you can understand from there here. So see here, if let us suppose there is a coolant and coolant will absorb the heat. So coolant become very heat, and when coolant will pass through this pipe, and after that this hot coolant will just exchange the heat through the nearby the water, and this water will again become steam due to its heat energy. You cannot you can just think that there is an enormous amount of the heat energy, right? So what will happen? This steam will again regenerate the electricity, and it will move the electricity to run the electric generator. I hope you have understood this. So this is the way. Now next is shielding. Shielding is very important. It is the protective covering made by a concrete wall protect from the harmful radiation. Apart from this, this is very dangerous because it will always release the radiation. So the lots of precautions has been taken. Lots of precautions has been taken to prevent radiation. Now next is our now next is your nuclear fusion. Nuclear fusion is the phenomena of a fusing two or more lighter nuclei forming a single heavy nuclei. For a fusion to take place, two nuclei must come close enough so that attractive short-range nuclear force is able to affect them. And since both the nuclei are positively charged particles, so they experience a Coulomb's repulsion. Therefore, they must have enough energy to overcome this. So, whenever how nuclear fusion will happen, so let us consider this: there is two lighter nuclei, and when just you will take it closer and give some sort of energy, so they will recombine to form a heavy nuclei, and it will release energy. It will release energy, right? It will release energy. Got it? Now from here we can say that this is a hydrogen 1 1 to form a hydrogen 1 having a mass 2 plus 1 electron as well as neutrino. Neutrino is the particle. After that it will release 0.42 megavolt. Now apart from this, when you will get this one hydrogen and one hydrogen, so it will mix up to get a helium 3 plus one neutron plus 3.27 mega electron energy will be released. After that again this hydrogen 2 having a mass 2, that is deuterium, will form 1 H3 plus 1 H1 and 4.03 mega volt of energy. So these are the reaction taking place in the form of a fusion. Now fusion of hydrogen and nuclei into helium nuclei is the source of energy of the most of the star including the sun. Whenever you will find sun or the stars, so you will see that they are using the phenomena which occur in the sun as well as stars are the nuclear fusion only, and by this process a large amount of heat energy is being released. Now, the thermonuclear fusion is the source of the energy output in the interior of the sky. The interior of the sun has a temperature of around 1.5 into 10 power 7 Kelvin, which is considerably less than the estimated temperature required for the fusion for the particle of the aberration. So, fusion in the sun involves proton whose energy are much above the average energy. That is, proton which are very high velocity fall on the Maxwell-Boltzmann distribution, and the fusion reaction in the sun is a multi-step process. It is not a single step process. So what will happen in this, which the hydrogen is fused into helium and the proton and proton cycle by which this occur represented by the following one. See here, this is hydrogen and it will form a hydrogen having a mass 2 plus electron plus neutrino plus 0.42 mega electron volt. After this electron E plus, that is proton and negative electron, will form a gamma radiation plus 1.02 mega electron volt. After that again one hydrogen 1 2 and 1 1 both will combine to get helium 2 3 plus gamma plus 5.49 mega electron volt. So finally we will get helium plus helium, again helium 2 plus 1 hydrogen plus 12.8. So these are the series of the reaction, and you can understand from this that for the fourth reaction to occur, the first three reaction must occur twice. So fourth reaction to occur, first three reaction must all three reaction must occur twice to get a fourth reaction, and this is your 4 hydrogen 1 and again 2 electron will provide you helium plus 2 neutrino. So this the symbol this symbol is considered as a neutrino, right? Neutrino plus gamma plus 226.7 mega electron volt, right? So from here what we can say that 1 hydrogen plus 4 electron gives helium plus 2 electron plus 2 neutrino plus 6 gamma plus 26.7 mega electron volt. So from the hydrogen atom combined to form a helium atom which will release 26.7 mega electron volt of the energy. As the hydrogen in the core gets depleted and become helium, the core starts to cool and the starts beginning to collapse under its own gravity, which increase the temperature of the core. So what happens as soon as hydrogen will drop, because hydrogen is being used for the fusion process. So what will happen? It will start cooling, right? And when it will start cooling, so what will happen? Star begins to collapse due to its own gravity, which increase the temperature suddenly, and this temperature is used for the again further fusion reaction. So in this way star will continue producing the energy. Now control nuclear fusion. The essential condition for carrying out the nuclear fusion is to raise the temperature of the material so that the particle have enough energy due to the thermal motion alone and they can overcome the Coulomb's barrier. This process is called thermonuclear fusion. So it means that for a fusion, so you have to give enormous amount of energy so that they will get combine each other, right? They will combine each other, right? They will get combine each other. Now the natural nuclear fusion is a star is a replicated in the thermonuclear fusion device, and the aim of a controlled thermofusion is to generate the steady power by heating the nuclear fuel to a temperature at the range of a 10 to 10 into 10 to the power 8 Kelvin. 10 to the power 8 Kelvin at this temperature, the fuel is a mixture of a positive ions and electron. So the challenge is to confine this plasma since no container can stand the high temperature. Several countries around the world, include India, are developing this technique in this connection. But it is very difficult. But in this, these are the things which will be used. These are the controlled thermoreaction fusion. So this is not a successful way to generate the energy, so we cannot use this. So mostly most of the power plants who is successfully generating the energy is nuclear fission only, not a nuclear fusion. Now if you want to differentiate the distincts between the nuclear fission and as well as fusion. So fission is the splitting of large nuclei into a smaller one. On the other hand, fusion is the combination of the two. It is the combination. So a combination means fusion, and fission means splitting. So this is fission and this is your fusion, right? Fission does not normally occurs in a nature, but fusion occur in a star such as sun. So fusion stars will occur, but fission doesn't occur in a nature. Fission requires critical mass of the substance and high speed neutron, but fusion high density and high temperature is required. So in fusion, in stars they require high density as well as huge amount of high temperature, but in fission it doesn't require. In fission, energy released is a million times greater in the chemical reaction, but lower than the energy released by nuclear fusion. Again, I am telling you, in nuclear fusion, like a star, the reaction which is occurring in the stars will release very high amount of energy. But if you talk about the fission, it will considerably release less amount of energy. But as soon as I will tell you the chemical reaction, while any release of the energy in the chemical reaction is always less than this fusion reaction or nuclear reaction, right? Uranium is the primary fuel for the fission reaction, and hydrogen isotopes are the primary fuel in the nuclear fusion. So I hope you have understood this. So this is the end of this class. So thank you. So I have completed all the nuclear this chapter, all the parts for this chapter. First part, second part, and third part. I have already covered this for the class 12, and this will be very much helpful for your board exam. Thank you for watching my video, and if you want further more videos, just please comment. Thank you.